So, how are things going for you guys? Yeah, let's just talk about calculus rather than life in general. I know it's early. I know everybody's tired. Yeah. So things are going okay so far. Do we pick away a little bit at the homework, the first couple of problems? Yeah? Is there questions on anything that we want to talk about before we pick up where we had left off? Mia? 7B, as in boy. Yeah, what page are we looking at? Like page 6 or something? 2? 82. Oh, yeah. 82. Right, we're in chapter 2, not chapter 1. That's right. All right. Okay. So for 7B, you're given a table of times and then displacements. And in part A, you're asked to find like the average velocity for a couple different intervals. And in part B, it says use the graph of those points to estimate that instantaneous velocity. So you could do a couple of things. One thing you could do is you could kind of just do this by inspection, where you could plot the points on a scatter plot and then try to sketch in the tangent line and just kind of estimate the slope of that thing. That would be okay. Probably what I would do with the information that you've been given is I would probably take the interval for 2, 3, the average velocity for that, and then the average velocity for the interval for 3, 4, and then probably average those, and that'll probably give you a pretty good estimate as well. Or even you could like take the points in that table, construct a scatter plot, and then use the equation for the scatter plot to do, there it goes. To do like, what we had done in kind of that first example. That's, I think, quite a bit of overkill for a problem like this, but if you wanted, you could do that. That would be appropriate as well. Does that feel okay, Mia? So lots of different ways, at least this point, to go out and make an approximation, right? As we go deeper in this, we'll actually algebraically show you how to find precisely these limits.
And you're saying one of the best ways is to work on a graph?
I think probably the best way for this problem is to just take the interval 2, 3 and the interval 3, 4 and take the average of those average velocities.
Right.
Just take those two numbers and add them up and divide by 2, and yes. That'll be a good estimate. But that's probably sufficient. Boy, this is we're being spotty today here, folks. Okay, just monkey around with this a little bit. Okay. So let's pick up where we left off then. Yes? Sergio, this came in for you while you were gone. All right. So I think last place we left off, we're just looking in section 2.2, and we've been just kind of working on evaluating limits of things, right? And at this point, our only techniques are using a graph, looking at the graph, or looking at the table, right? Those are basically our two techniques we have to evaluate a limit. And I think where we had left off last was we had looked at this example. And we saw that this limit did not exist, right? So let's take a minute and use this as a jumping off point to develop a new concept. Okay, so if we remember when we looked at the graph of this thing, these. Oops. And we'll zoom in right close to 0 there. Oh, what did I do? Did something. Oh. That would be why. Wasn't looking. There we go. Everybody kind of remember we did this a couple of times and zoomed in and just kept getting funky behavior the whole way. What I'm going to do real quick is I'm just going to turn off the axes and hit graph again. So I've just turned off the X and Y axes. And you see how like this spot where the gap is X equals 0? You see how one end of my limit appears to be going to one value and the other end of my limit appears to be going to another value, or one side of 0? We're going to define that concept as a one-sided limit. So what is the left side of the happen, or what's going on to the left side as we're approaching our limit, and what's going on to the right side as we're approaching our limit? Everybody okay with that idea? Okay, so let's go ahead and define that, because this is the first example of something we've seen where it didn't seem like the left-hand side and the right-hand side of the function were approaching the same value. Does that, everybody feel okay there? Okay. So to denote that, we're going to say we're going to call this the left-hand limit. So that's that value L would be the value the graph is approaching from the left as X approaches A. And we'll use that little plus sign in the exponent to designate the right-hand limit. Everybody's okay with that notation? Now, what can we say about the right hand and left hand limits with respect to the limit of the limit of, like, the left hand limit as x approaches a and the right hand limit as x approaches a? What does that tell us about the limit as x approaches a? Yeah. So what does the left hand limit and the right hand limit tell us about the limit? For the limit to exist, the right hand limit and left hand limit have to match. That's basically all we're saying, right? As in the previous graph here, we saw that the left hand limit and the right hand limit weren't going to the same value, and the limit failed to exist there. So that's what we're going to say now. So let's formalize that, right?
Is that the same value? The limit doesn't exist?
Yeah, so here's what we're going to say. We'll call this a lemma. A lemma is like just a fancy math word for like a minor theorem. So we say the limit as x approaches a of f of x is equal to L. I don't know what is up with my stylus. It's been such a pain. If and only if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x is also equal to L. So what's that's saying is that if a limit exists, then the right hand limit and the left hand limit have to match. Or if the left hand limit and right hand limit matches, then the limit exists and it has that same value. Which is intuitively makes a lot of sense, right? Like that feels like the way it should be. So let's look at a graphical example here and just kind of apply that idea. Okay, so we have this picture of some function f of x, and we're asked for two limits. The limit as x approaches 2 and the limit as x approaches 5. Notice that each of those locations our function is discontinuous. Everybody's cool with that? And in fact, we're undefined entirely at x equals 2. Everybody's cool? So what would we say in this case the limit as x approaches 2 is? What is that limit? So the first one, the limit as x approaches 2, would be what?
defined.
Does not exist. That is correct. Because if we look at the left-hand limit,
Have two on the same.
that's 3. Maybe we'll use a different color. But if we look at the right-hand limit, that's 1. Since those do not agree, the limit there cannot exist.
Yeah, why did you put 4 there?
I meant 3, sorry.
1 plus 3 is 4.
Because it's 8:04 in the morning and we're doing complicated mathematics.
Doesn't exist. That's okay.
Math at 8:04? Somebody's got to take it. Does everybody feel okay with what I evaluated the left-hand limit as and the right-hand limit as? And why the limit there fails to exist because of that? Is that okay? Let's do 5. What's the limit as x approaches 5? 2. Very good. So if we look at the right-hand limit, that's going to 2. And if I look at the left-hand limit, I'm sorry, I flipped them around. The left-hand limit was the first one I drew. The right-hand limit was the second one I drew. 8:05, still not getting any better.
Wait, there's
Wait,
still
Mr.
2
Cole,
4s.
you really lost.
I'm just writing the wrong numbers.
But you like 4 a lot.
Apparently, yeah, I'm stuck on it. We got to work some 4s in so I can
I'm
stop.
sorry, I just like.
Nope, go ahead.
I just got really confused. Can you like explain like how like it's or what does D&E stand for?
Does not exist.
Yeah, does not exist.
Okay.
And then like how it equals 2. That's
Yeah. So if I look at the left-hand limit at x equals 2,
right.
that's 3. If I look at the right-hand limit, that's 1.
Oh.
They're not the same
They're
limit,
not the same limit, so it doesn't.
so it
exist.
doesn't exist because it's
Okay.
disagreeing.
Right.
If I look at x equals 5, the left-hand limit is 2, and the right-hand limit also 2. Those ones agree, so the limit exists.
Perfect.
It's 2.
Okay, now I understand.
Now note that it didn't matter that f of 5 is actually 1. Right?
Why?
Because it's not connected.
Because there's a point.
Yeah. Do we have that 1 point there? That's the point 5 comma 1?
Yeah.
Right? So that's saying that f of 5 is equal to 1,
Oh, yeah.
even though the limit as x approaches 5 is 2. The limit does not need to agree with the actual defined value for the function, particularly if there's like a discontinuity like this, like a
So
jump
on the
discontinuity.
calculator, would this be like a 1.99?
Yeah.
It would say like, would there be like an error on the time?
So if you did, okay, so one thing, first of all, if you had an you could not have an equation on your calculator that's going to give you this function. You could not type it in and have it give you this behavior. That's why I went with the picture and just defined it with the picture rather than an equation. But yeah, if you were trying to, if you had an equation that had a removable discontinuity like this, and you did the table, you'd go, would be like 1.999 or 2.001 or something, would be the, if you got values appropriately close to 5,
So it won't say 2.
it won't get to 2. I mean, I guess if you pick like so close, the calculator just rounds up because it loses the float. Like your calculator can only hold so many decimal places, and then it just has to like kind of guess.
Here's the limit, so it can never get to 2, but always approach it.
Right. Yes, exactly right. Yes, precisely. Do we feel okay with this idea? The left-hand limit and the right-hand limit? It's okay? Again, not a difficult idea, but like the notation's a little different. It's new vocabulary. Intuitively, it makes sense that for limit to exist, if I approach different values from different sides, that's the problem. Which one do I call the limit, right? Okay. So the next thing I want to talk about are infinite limits. So let's just say we look at the limit as x approaches 0 of 1 over x squared. So let's look at that in our calculator.
Oh, that's gonna be like a reverse one, like a rainbow.
Oops, forgot to turn our axes back.
Turn the back.
Sorry,
Oh, alright.
alpha y equals option 1 will give you the fraction. So if I look at what's going on here at x equals 0, what does the graph appear to be going to? Positive infinity, right? It's getting up, going up bigger and bigger and bigger. Let's just kind of do that tabular, right? Let's look at the table. So I'm going to look at some values that are very close to 0 from the negative side. So like negative 0.001, or 3 O's in 1. Oops, I didn't mean y1 though, I meant y2. Excuse me. I put mine in y2. I was like, that didn't look right. So negative 0.1, negative 0.01, negative 0.01. What do you see happening here as I'm getting closer to 0? It just keeps getting bigger and bigger and bigger, right? No, the closer I get to 0, the bigger that's going to get. And if you wanted to go check from the other side, from the right side as opposed to the left, because we should double check to make sure they agree, I'm getting the same behavior, right? Everybody agree with our assessment that this is going to positive infinity? Okay. And now intuitively, if we then wanted the limit as x approaches 0 of negative 1 over x squared, what do you think that limit's going to be? Negative infinity. That's correct. What would the graph have looked like? The same thing flipped upside down, right? So just to demonstrate that to you, just tack the negative sign on there, pointing down now instead of pointing up. Everybody's cool? Okay. How about the limit as x approaches 0 of 1 over x? Can anybody predict what that's going to be without actually graphing anything? It's not going to exist.
Oh, I got it. There we go.
So what you'd want to think about is if we just have 1 over x like that, come on. Any negative values of x, as they get closer to 0, are going to go towards negative infinity. And the positive values of x as they get closer to 0 will go to positive infinity. So the right-hand limit and left-hand limit won't match up. Oops, I wanted to stop. I've got to turn that other one off. So again, we have negative values. Any negative value you plug in is going to give you a negative number. As those negative values get closer to 0, it's going to go towards negative infinity. Any positive value for x you plug into 1 over x is going to return a positive number. So the positive side, as you get closer to 0, is going to go towards positive infinity. We notice the left-hand limit and right-hand limit don't agree. So we would say that the limit here does not exist. Is everybody feeling okay with what we're doing? Notice in all three of these situations, though, whether the limit was, or whether you're talking about 1 over x squared, negative 1 over x squared, or 1 over x, all of those have a vertical asymptote at x equals 0, right? All of those functions had a vertical asymptote at x equals 0. So what we'll say then is the following. Oh boy. I think my computer just needs a resetting in a bad way. So x equals a is a vertical asymptote if and only if at least one of these statements is true.
After x equals a?
Is
Oh.
so if the limit at x equals a is either positive infinity or negative infinity, then that would make a vertical asymptote, like we saw in examples A or B. Everybody agree with that?
That's disgusting. I just popped a mosquito and I got like blood all over.
Thanks for sharing.
Welcome. You're welcome, everybody.
Then don't go by Paul.
Like, okay, that's disgusting. Like, it was so big, and it just like. Die.
You caught him right after Thanksgiving dinner, huh?
Yeah.
Or if the left-hand limit gives you negative infinity or positive infinity, that should be a vertical asymptote. Or also, if the right-hand limit is either positive infinity or negative infinity, that should also indicate a vertical asymptote.
Is this a vertical asymptote at 0?
X equals a, right? X equals a. Yeah, wherever the vertical asymptote wants to be. So in the previous example, it was at 0 in all three cases, right? Does that feel okay to everybody? Okay. So using this definition then, we could do things like show this function f of x has a vertical asymptote at x equals 3. To do that, what would I need to do? I need to show one of these three things from above, right? Any one of those three would be enough. So Sergio's instinct to look at the graph initially, I think, is a great first step. So let's go ahead and do that. And here's one where using that fraction command to type this in will be really helpful, because you have to muck around with a bunch of parentheses to get this to come out the way you'd have, the right way if you don't. But
What's after VA?
at
Oh, that's at.
x equals 3. Okay, so there's our graph. Notice here that at x equals 3, the right-hand limit appears to be positive infinity, and the left-hand limit appears to be negative infinity. Everybody agree with that? So that meets both criteria B and criteria C. Just one of them would have been enough, but we have both, which is fine. So we have that the limit as x approaches 3 from the left of f of x was equal to negative infinity. Or you could have said the limit as x approaches 3 from the right is positive infinity. That would also be enough. Either statement would be fine, or you could write both of them, still fine. Everybody's okay? Victoria?
How do you know it's not the other?
Because the right-hand limit is positive infinity and the left-hand limit is negative infinity,
Okay.
so that I would know the limit at 3 doesn't exist. So, but I do have the left-hand limit and the right-hand limit being infinite, which is enough. Is that?
Yeah. Just, you know how you had the graph and you're just going like this?
Mhm.
Is that what the first would be?
Yes. Yeah, it would be a situation like that.
Okay.
Yes. Sophia.
Why is it not, does not exist?
The limit as x approaches 3 does not exist.
Okay.
You're correct. But that alone isn't telling us that there's no vertical asymptote, or that there is a vertical asymptote.
So we don't care.
We don't care about
For
that.
the way this question is written.
Yes, exactly.
We're just trying to find. Where are we trying to find out?
We're trying to show that there's a vertical asymptote.
Just show that there is.
Yes, we don't have to find it. Even well, we did.
Gave it to you.
Oh,
In the problem, it says x equals 3, right? So we're just kind of proving that that is the vertical asymptote.
okay.
And the way we did that was by using our definition
Right.
and showing that either the limit, the left-hand limit, or the right-hand limit is infinite. Any of those is enough to show a vertical asymptote.
Yeah, I pause. Yeah, true.
Next example, find the vertical asymptote for the tangent function. So our function in this case would just be like f of x equals tan x. Okay. Trig recall. What trig identity could we use here that might be helpful? Tangent is sine over cosine. Why would that be helpful?
Oh.
This is a fraction, right?
Yeah.
So whenever cosine is 0, we're potentially going to be having a vertical asymptote, right? When is cosine equal to 0? Yes. That's the first place on the unit circle. Oh no, not pi.
Yeah, no, I was gonna say that.
Pi over 2.
Yeah, there we go.
And 3 pi over 2. You might be in degree mode instead of radian mode
No.
if you're trying to graph this.
Yeah. Like in the line.
Yeah, those are the asymptotes.
No, like in like the squiggly line, there's just like a random rate.
Okay. I'll take a look at it in a minute. Okay. So we can say the limit then as x approaches pi over 2. So, okay. So like then we want to show that, so let's just say x equals pi over 2 is a VA. That's what we're going to try to show then, right? So if we look at the graph, let's take a look at the graph. So we'll do tan x. I'm going to make sure that I'm in radian mode since I'm graphing a trig function. And then I'm just going to do zoom trig. And that'll reset my window so that it's going from negative 2 pi to positive 2 pi, and all the tick marks on the x-axis are by pi over 4, I think. Double check that real quick. Nope, they're by pi over 2. So here's 0, here's pi over 2. That's an asymptote. So notice the left-hand asymptote goes to positive infinity, and the right-hand asymptote goes to negative infinity. So either one of those would be enough to state that that is the vertical asymptote. Everybody's okay with that?
Yeah, why did you say it was negative pi over 2? I thought you were
That's the left-hand limit, right? When the negative sign is in the exponent like that, that's talking about the left-hand limit. Just like if the positive sign was in the exponent, it would be the right-hand limit.
So does it matter which one of these lines you're looking at?
No, I just picked the first value from the unit circle.
Could it also be like
There's,
positive infinity and then positive pi over 2?
yes, that would also be fine.
And could also do like 2 pi over 2. That one?
3 pi over 2 would also be fine. Sophia.
Couldn't pi over 2 also be the right-hand limit for a different line? That makes sense.
Couldn't pi over,
Yeah.
It's the same.
So like pi over 2, because there's the line that goes through like 0. Yeah.
so you're talking about this piece.
Yeah, so couldn't pi over 2 be the right-hand asymptote for that one?
So it could be the right hand for this piece.
For that one.
Oh, did I write the wrong thing here? I did. Here, this was, Oops. That's positive infinity, excuse me. That was your issue, right? Yes, thank you. Yes. So this was supposed to be a plus sign, was what Sophia pointed out to me.
Right. because you're-
If I look at the left end of this, that was pointing up.
Wait, yeah, isn't that the right side?
No, because it's in the bottom of six.
So this is,
If you're pushing the.
The right side go up.
no, you're looking at pi over 2, not the curve. You're looking at pi over 2. So this is the line pi over 2, correct? The left side of the graph is this piece. The right side of the graph is that piece that are on different curves.
Average sense.
Okay? Did that straighten it out?
Yeah.
Okay, good. Again, these are the type of clarifications, like you guys need to understand that, right? So if you're confused or you're not sure, ask, that's okay. Sergio and then Victoria.
This is probably a stupid question, but how did you know that line exactly was pi over 2? That was 0 and then the next.
Well, the tick marks are at pi over 2 on the graph. So when I did the zoom trig,
Right.
I know it's going up by pi over 2. That's
Oh, and it's the
1.57,
first one.
and that's the first one. So it's positive pi over 2.
How did you do that?
It's just, you literally just hit
The-
zoom when you go down a trig.
So if you pick zoom and then option 7 is trig, it'll just reset your axes.
Oh, wow. Oh, that's
Wait, then you just go zoom standard, which is like 1 more, right?
Yeah.
Wait, so you said like the top one is the left and then the bottom is the right, well, like, is that just something like?
So pi over 2 is here, correct? This would be like the vertical line for pi over 2.
Yeah.
So the left side of pi over 2 is this part of the graph. And the right side of pi over 2 is that part of the graph.
That's just how it is,
It's just left hand, right hand, just like your hands. You know what I mean?
yeah.
So it's just left and right. That's all we're talking. Is that okay?
Yeah.
Okay. Again, I don't want to make it any, like it doesn't need to be any more complicated than that. Like we're just looking at a picture, what's going on to the left of this spot, what's going on to the right of this spot. You just find the spot, look what's going on either side.
Does that say limit? Wait, X?
That's the natural log, ln.
Oh, LX.
No, it's not.
This one is log base E.
Yeah, exactly. It's not log base 10.
Yeah, it's log base 10.
No, it's not.
ln is log base E. Regular log with no subscript is log base 10.
What mode should we put our calculator in?
Doesn't matter.
Standard.
Sure. So I'm going to turn that off. I'm going to do log of x, natural log of x, I guess I'll say. And then I'll do zoom standard. So there's my curve for the natural log of x. I'm going to just turn off my axes real quick so you guys can get a little bit better feel for what's going on. So what do you guys see?
Well,
There's only one line.
yeah, so
There's only one side, right? To the left of 0, nothing is going on.
yeah.
So we just have to worry about the right side of 0 and see if that actually approaches maybe negative infinity, it looks like, maybe if it's going actually all the way down. Maybe or tabular might be the better way of looking at this. Does that sound okay to you guys?
Negative infinity.
Yeah.
It'd be positive now.
Not if it's approaching 0, because
Right,
you're
it
going
stops.
this way. Well, let's see.
Oh, I see.
So your calculator has only so many pixels.
Oh.
So your calculator can give you graphs that don't actually, this looks like it has a decided start and stop.
Right.
But if I try to do the natural log of 0, what do I get? Undefined.
Yeah, I got error.
Yeah.
Zero, so.
So let's see if I go and I go approaching 0 from the right, what ends up happening. That was that 7, I think? So maybe we'll start at point 1. Okay. I guess I wasn't on L7 or Y7 yet, huh? Go down and look again. 6. So the natural log of point 1 is that. And then if we go to 0.1, it's that. If we go to point 0.01, still getting smaller, right? So your calculator can give you misleading pictures because it has only so many pixels. Let's get real close to 0. Oops, no 3 there. So it just keeps getting smaller the closer you get, right? So what can we say? Yeah, the limit as x approaches 0 from the right of f of x equals negative infinity.
Wait, so why wouldn't that just be like, yeah, why wouldn't that just be like the first option where it's just like there's no positive or negative on your A? It's just,
There's no left.
Because if I look at the left-hand limit,
right.
what is it?
Nothing.
Okay.
Nothing. That doesn't agree with negative infinity. There's no part of the graph. This
yeah.
graph only has a right-hand limit at 0 because there's no part of the graph before 0.
Right, I see.
So
Okay.
what if it did have? How do you tell it has to stop?
Well, if you did natural log of 0 and you came up with a number,
Right.
that's a stop. It has a specific value at 0.
I see.
Mia.
So for criteria A, would it have to be that there are two sides with their equal?
Yes.
Okay,
So like 1 over x squared would be criteria A. Or you could, and here's the thing, you could use criteria A there, but B and C would work in that situation still.
how did you use A? It's like, left.
No, what I'm saying is for like 1 over x squared,
Oh, yeah.
anytime A is you could use A as a criteria, you could have just used B or C. Because if the natural log of, or the limit as x approaches A of f of x is equal to infinity, then its left-hand limit and right-hand limit were also equal to infinity, which would have been enough. So really when we're searching for these vertical asymptotes, just gonna look at the right-hand and left-hand limits primarily. That's enough. I don't really need to know what the actual limit is.
Wait, so with this, the limit for this, could it be like the opposite, could it be like x going to 0 and then left hand or no?
For part C, there is no left hand, so no, it had to be from the right. Had to be the right-hand limit.
So do you need to write the limit of x approaching 0 to the left does not exist?
Nope.
Do you just not?
All you need is one side of the limit to go to positive or negative infinity to show it's a vertical asymptote. That's all you need. Don't give more than you need. There's no points for overkill. You did it or you didn't. It's proved or it's not. Okay. So far, so good? Still doing okay? All right. So today we're going to start escaping from graphs and tables being our only ways to evaluate limits and begin to be able to do this algebraically, which is the way that makes life a little bit easier, but doesn't build a lot of intuition. So the graphs and the tables are nice because even if you don't understand like what it is you're looking at, you can kind of intuit the answer. Here, algebraically, we're going to be able to do a lot without having to write a lot, without having to go and graph the thing or build out a bunch of points in a table. And look what's happening. We're just going to be able to manipulate symbols.
That sounds pretty good to me.
Yeah.
We have
So
another one.
let's see. This is 2.3. So we're going to look at a whole mess of limit laws here today. And this little preamble is going to exist for each of these next, what do I got? I got like 9 limit laws here to start with. So suppose that we have some n's and c's that are real numbers. And then we'll call these our constants. And the limit as x approaches a of f of x and the limit as x approaches a of g of x exist. Then we have the following.
Are those both x approaches a? Or x equals a?
X approaches a for both of them. Yep. So keep in mind, the thing that's we have to be careful about is the assumption that those limits exist, right? So the limit for these limit laws to be able to be used, the limit has to exist, or else you can't muck around with it the way we're about to. Okay? That should pop back up in a second. Okay, good. So you have the limit as x approaches a of the sum of two functions. Well, that's equivalent to taking the limit of the first function and adding it to the limit of the second function. Basically, what are we seeing here? That the limit can distribute, right? Everybody's okay with that notion? Seems fine, right? And actually, let's do this. If it's subtraction, also works. So I'm just going to turn that into a plus or minus. So that would be limit laws 1 and 2. Everybody's okay with me being compact there, rather than writing that all again, especially with as finicky as my stylus is being today. Okay, the next one we have the limit as x approaches a of c times f of x. Remember that c is a constant, so something like 2 times or whatever. So what we can do is we can pull that c out front of our limit. Since there's no x involved with c is just a constant, you can move it outside of the limit. That's c times f of x. Is that okay? It's supposed to be the multiplication dot. I know, everything, I'm doing the best I can with my limited penmanship abilities.
I think it's good.
I wanna like try mine.
No, I mean like literally just my ability to write well is.
It's kind of impressive how you can write like a straight up like angle on a moving.
I was really wondering how you were doing that. Like writing like that.
I know, but I still like to have like the keyboard access because I end up feel like I don't know. I feel like I need it still. But anyways, keep on going. Again, I said I think I have 9 of these. And then we'll do some examples where we'll apply them. So we have the limit as x approaches a of f of x times g of x. So the product of two functions. What we can do then so the limit of a product of two functions is the product of the limit of each function.
You don't need to get like
Is everybody okay with that? Now this is a little different, right? We don't see a lot of cases where if I have two things multiplied together, I can do the thing outside of the multiplication first and then multiply them. That's a little strange. Will that is a super fair question. When I get to the examples and we start like being able to bang through some of these limits without actually even having to draw anything or look at it, do any tabular things, it's going to be helpful. And remember that this limit is just a tool, a stepping stone on the way to our first major calculus operation. And we do not want to be doing it all graphically. That's what Newton was doing, and nobody does it the way Newton was doing it.
yeah, sorry, that was very
No, it is okay to ask those questions. Because again, getting an idea of like where this is going helps you pay attention, helps you understand what it is you're seeing. Sergio?
Which one do we do first? Which calculus operation?
The derivative is the first.
That just sounds good. Yeah, it's only one I know.
There's in this course, there's only 2 calculus operations you're going to use.
Hallelujah.
It is the derivative and then the integral.
Yeah.
Oh yeah, I heard it.
Thanks.
So, yeah. I know. It'll pop up back in a second, I think. So if I have the limit of a quotient, I can just take the limit of the numerator and divide it by the limit of the denominator.
So if A is different in the that matter? Or would it not be different?
Well, if you look at the right or the left-hand side here,
Yeah.
there's just one limit and it's to A. So you're just taking that same limit, you're just breaking it onto both functions, basically. The key is that limit for f of x and that limit for g of x have to exist for both of them in order to do that splitting.
Because if it don't exist,
If it doesn't exist, then we can't do that splitting, because you can do this splitting and get all kinds of goofy results that aren't real.
How many of these properties is there?
I think I said 9.
Sorry, you guys.
I know. This one is quite useful.
alright.
So what that's saying there is, if I have a function to a power, and I'm taking the limit of that, I can just find the limit of the function itself, and then raise that answer to the power, which is, like imagine having x minus 3 to the 15th. It's like, yuck, I don't want to have to muss around with expanding that out. You can just do the limit of x minus 3 and then take that answer to the 15th, which is super helpful in terms of cutting down the amount of algebra crap you'd have to sort of sift through,
That's pretty cool.
right?
I like that.
Yeah, it's quite nice. And again, we're going to get to some numeric or actual real examples where we're going to show you how we use these. So limit as x approaches a of c. Is there an x anywhere in this? What do you think the limit's going to be then? Just c, right? The limit of a constant is just the constant. Yeah.
That's cool.
And
What was good?
here is one that is also quite helpful. The limit as x approaches a of x is just a. We just plugged a into our function. And why didn't they do that here? Is that something we did later? Oh, yeah, okay. We do that later. It gets a whole special name. Okay, that's why.
Not x minus.
What is that?
X equals 1.
Which number?
Never mind.
Okay. And then our last one here, if you take the limit of a radical of a function, again, you can ignore the radical, just do the limit of the function, and then take the radical of your answer. Again, quite convenient,
Yeah.
because it allows you to work on the simpler thing, get a number, and then just do the radical to the number. All right. Let's do some examples now. Okay? So I'm just going to walk through the first example, and I'm going to do this really slowly. And I'm going to say the name of the property that I'm using in each case as I manipulate my way through this. Okay?
Wait, Mr. Coolidge.
Yes.
Sorry, but is that X like approaching 5?
Yes. 5. Yep.
So are we like expanding first? Is that like how we're
Not quite.
So would the first thing you do move like the exponent outside?
No, because the exponent isn't applied to the entire function.
Right, okay.
So the first thing I would do is use properties 1 and 2.
Oh, for the plus and minus.
So I'm going to write this as 3 separate limits.
Okay.
The limit of x approaches 5 of 2x squared, and then minus the limit as x approaches 5 of 3x, plus the limit as x approaches 5 of 4.
Because you guys thought an exhaust pipe was
Everybody's okay with that?
Yep.
Okay. If I look at now this first piece, the next thing I would do is apply property 3 and take that coefficient of 2 and move that out to the front.
Oh, did you go through these in order?
Not necessarily.
Does it matter the order?
Just in terms of like order of operations,
Okay.
kind of matter, but
Not too much.
I would apply that property 3 also to the second limit.
It's very important that we know what where
And then I'm going to apply property 7 to that last limit. Since we're just taking the limit of a constant, that limit is just the constant. Everybody's still doing okay?
Where? Explain the last one real quick.
The limit of a constant is just the constant.
Oh,
Yeah.
I got you.
Before I leave, do I just walk out?
That's the 7.
What's up?
Before I leave, do I just walk out or do I have to go to the office?
I think you're probably supposed to sign out at the office.
That's the 7th rule, right? The constant one?
What's that?
7th rule.
Yes. Yeah. Okay. In the first limit, what I'm going to do now is that property 6. That's going to allow me to move that squared outside of the limit. And then on the second limit, I'm going to apply property 8 that allows me to replace the limit as x approaches 5 of x with just 5.
What rule did you use on minus 2 limit at? Like the second one?
I used property 8,
Okay, that says.
which allows me to just substitute a in for x.
So whenever x is alone, you can do that?
When x is alone, you can do that, yes. Okay. And now if you notice, if I look at the inside here, I have the limit where x is alone. So I can replace that with the 5. So 5 squared is 25, times 2 is 50, minus 15 is 35, plus 4 is 39.
I love that. Awesome. Yeah, solid number.
Does anybody make an observation about what we really just did here?
Not at all. Oh, we did like. We didn't calculate.
That's giving log.
We just did calculus. That's what we did.
39. Does anybody notice anything about 39?
I'm trying. I have no idea.
Yeah.
Oh, nice.
What did we really just do?
Just plug in 5.
We just plugged 5 into the function. This is a property.
So why did we do all that?
These things become useful when you. Well, yeah. If you have, so let's say you have the product or sum or difference or something of functions, and that limit is undefined, like it does not exist. You can still break it up into pieces and like maybe to manipulate it so that. Anyways, we'll see an example in a second. Let me write down this property and then I'll get to your how do you know, okay? I definitely want to answer it. I'm just like midway through and I don't want to lose my spot. Because we're just about out of time, right?
What if we just like
Later, Serge.
Where are you doing that?
yeah.
I feel like I'm learning.
Sophia. Okay. If you need to ask a clarification, you're welcome to do that still. So, on all these problems like we had done before, if you want to do the limit of something approaches 7, what's the first thing we should now try doing? Just plugging 7 in and seeing if it comes out to be a number. Right? If it's undefined, then there's more that we might be able to do. But initially, if you're given a function equation and you're taking the limit as it approaches 7, you plug that stuff in and just see what happens. If you're given a graph or a table to represent your function, that's a different story. But if we're given an equation and we have like the limit approaching 8, first thing I'm going to do is plug in and see what happens if I plug 8 in. Yes, sir.
So the homework, like part 8 has like 8 different subparts. Do we have to do each of those subparts? Part 8?
For which?
For 2.1, number 3.
2.1, number 3? Yes.
Part 8 has 8 different subparts.
Yeah, I think it's just asking you to find like a bunch of different average velocities or something. 1A, you said? Oh, no, you're looking at...
2.1.
Oh, 3A.
3A has like 8 different.
Yeah, because those are... And again, all you need to do is just like write down what you got off your calculator. Just like practicing using a table to evaluate a limit. And it's just giving you the values to build your table with. You know what I mean? You can just like write it in a list. There's nothing... You don't have to show any work for something like that. That's absurd. And in fact, I would just type the function in my calculator and just use like y1 of, and just bang through all those on my calculator and just write down the numbers. You know what I mean? Okay. Just FYI, guys, the 2-2 homework was 3 through 5, 7, 9, 11, 13 through 14, 15, 17, 21, 27, 31 to 43 odds, and then 47 and 54. I'll get all that stuff up into my Notre Dame as well on the as part of the assignment name or whatever. And we finished 2-2, so you guys should be able to do these now there's a long list of things. A lot of them it's just going to be like looking at a graph and telling what the left-hand limit or right-hand limit is from the picture. So like it's not super time-consuming stuff. You guys can go as well. Thank you. Have a great day.